Alright, we are going back to the basics with this one. I haven't used this music track in like forever, but I used to use it all of the time when I was first streaming. I still occasionally use it, but usually this one is my go-to one. Wait a second, do I have my pointer showing? Let me just check real fast. That's the wrong thing. I am not capturing my cursor. Okay, yeah. Anyways, this is the one I usually use. Yeah, when we were filming footage for the Horizon world that my team made, turned off cursor recording, and I apparently forgot to turn it back on. So it's a good thing that I remembered to turn that on before we get back into coding in Vim. You know, it's very important that I have my cursor showing when I'm coding in Vim. Essential thing. Alright. Anyways, by the end of the last stream, so last stream we streamed for 5 hours, I was figuring out, you know, what direction am I going to go in with the game engine, and after 5 hours, we came up with the term component graph system. So, I independently figured out the sort of architecture that I want to use, and after like designing this from the ground up, one of my chatters was like, this sounds like a component tree system that like somebody was talking about a while back. And then after like doing a little bit of searching, a little bit of testing of different names, we figured out that it was actually a component graph system, because this is all the way back in 2017 that this was being talked about. Yeah, this repo is the only, like, aside from references to this repo, this is the only, like, talk about this concept of a component graph system. And I've been, like, doing a lot of research on it after the fact, because it seems I have independently come up with the idea of something like this, kind of through a similar route to what this dude did. So this dude that made this also made one of the popular ECS libraries for Rust. It's somewhere in here. It's like the... Anyway, I'm not sure where it is. Here, let me actually start this real fast. And yeah, so it's like very unexplored concept that I've just like naturally found my way into. Now, I will say that if you go to this repo and you read through this document, I think, no, not to like talk myself up or anything, but I do think I have a better understanding of ECS than the original authors of this had. Because there are a little bit of inconsistencies in the way that they explain how the system works. And I agree with, I'm gonna say 70% of it, because I'm not actually sure how much of it I really agree with. But I do like the actual just base idea structure, so I don't think I'm actually going to reference this code base very much at all, but it is comforting to see like, oh, somebody else came up with similar ideas, and when they did do something with this, and because this is like a test of the concept, they didn't really use it for anything real, but they did do benchmarks, and there's Froggy, and you can see that only this one other... Well, actually... No. It is the fastest one on this benchmark. I didn't realize that. I didn't actually read the numbers. I was just like, oh, there's like... This ECS is faster than it, but it's in second place. No, it actually is the fastest one on this benchmark. Unless we're doing build. Smaller is better. Okay, yeah. Specs, which I think is the other one this author made, is a good bit faster. Or, no. This is the build times. This is the actual, like, running. This is the build times, I think. Do they actually say what they are? Anyway, I'm going with, this is the build times, and this is the actual runtime values. Anyways, it doesn't really matter how fast it is, because I think inherently a component graph system is going to be a little bit slower than an entity component system, simply because entity component systems are objectively the best architecture to take advantage of SIMD optimizations. So that's when your CPU has some instructions that are able to operate on powers of 2, usually 4 and above, numbers of variables at once. So you can add 4 floats to 4 floats at once. And yeah, and ECS is really good at, like, it's super easy to use SIMD optimizations in an entity component system. A component graph system breaks out of the data storage model that lends itself really well to iterating over components with SIMD optimizations. However, if I have been thinking about this because I'm like, oh no, we lose the potential to eventually update Brane script to be able to do SIMD optimizations. But I've been thinking, since we're already doing checks on the graph to see ahead of time if certain reference chains of components would cause blocking operations, you could piggyback off of that same walking of the graph to also see how you could group components together in such a way that it would not stall the pipeline substantially to wait to update those components until you could update the components in a batch. So I think eventually we will be able to do SIMD optimizations with the component graph system, just not to the degree that you could with an entity component system, potentially. Everything evening out, I do think that this is going to be potentially the fastest possible architecture that we could code for this scenario, while still allowing it to be sandboxable and hopefully easy to work with once we've abstracted the fact that objects don't exist in the system. In a component graph system, there are no entities. There's no concept of I have an object. Instead, it's all the little features that you would usually make up an object just kind of spread out in a graph and all referencing each other. And as data filters through that graph, you get things that look like objects that emerge from that. So we're going to need to abstract that slightly to make it easier to work with. Now, all of that aside, that's basically what we figured out last stream and a little bit of what I figured out since that stream. But what are we actually working on this stream? We are actually coding this stream. Oh, imagine, it has been a month since I've touched this code base, and I don't fully remember where everything is. So I don't need this page anymore. This is all out of date. There we go, it's up to date now. Alright. And I think tasks is what we need to look at this precise moment. And what are the most important parts of the Brane script runtime? So for me, it was important to figure out what architecture we're using for the engine before continuing with Brane script, just to make sure that I didn't have to architect it differently than I was already planning to, so that I don't have to refactor it later. So design ahead of time so I can minimize the amount of core level architecture refactors. We'll probably still need to refactor some things to make them more efficient or work slightly better for unforeseen things, but we won't have to do sweeping architecture changes to add new features, theoretically. Here, if I... No, that... We don't have any in progress. Okay. So... I'm gonna add another status called next up. Just that way I can group, like, what do I want to do next reasonably without having this huge list of things. Okay. Scheduling system, we're not there yet. Allocator kind of function calls. Let's add. Can I call my own functions? Add function calling for defined functions. Add file-based module imports. Okay. Add static function linking. Do we emit pipelines right now? We don't emit pipelines right now. So we do need the ability to emit pipelines, import pipelines. Runtime reload support for Brane lift backend. Add static function linking. Fully implement templates. So, being able to call our own functions, fully implementing templates, those are kind of, those happen at the same time. Ooh, I need implement read only. Implement bindings fully. This is kind of what we need. We need memory bindings for to-do list. We need memory bindings for I kind of want these to be their own individual things, but we do all of them at the same time. But we need memory bindings for read-only pages, functions, pipelines. Actually, yeah. Need memory bindings for read-only pages, functions, and pipelines. So, because I want the ability to be able to pass closures around the code base, we do need the base level ability to have a function, and then you store a function inside of an object, and then you have a closure. So as long as we have function pointers working, we're good to go. We might also be able to implement pipelines as a function pointer with a pipeline signature and just have it be understood that when that function gets executed, what we're actually executing is a pipeline, or that starting a pipeline, basically. But these are the main things that we need to figure out how to have bindings for. And I guess when it really comes down to it, this is the most important thing for us to implement. We also do need casting. We do need to add... We need to add casting. We need to implement bindings fully, like memory bindings fully. And then after we have bindings fully implemented, we can make an actual allocator, not alligator, allocator for those bindings. Casting is kind of just like it's there whenever we get around to it. Those are just like that's a busy work of adding a bunch of intrinsic functions. And we also do have to mess with our bytecode to do that. Can't even design pipeline dispatch before we actually emit pipelines. That might be important to do at some point. Okay, so it's time to design how do our pointers really work? Because I want to do a fun thing where implicitly behind the scenes, we have a bunch of pointers. Those pointers can be whatever value we need them to be. Like at the end of the day, it's just a int32 or int64. I think I might upgrade pointers to be 64-bit integers. And the reason I am thinking about doing that is because if we upgrade it to a 64-bit pointer, we have enough memory space to... do basically what the compiler does, not the compiler, the operating system, or maybe even the CPU itself, does to bind memory pages on the operating system level, but we can emulate that within the scripting language. So I did like a little bit of research on like, my original idea was like, oh, we want completely branchless checking of memory. It turns out on a modern system, branchless pointer indirection based methods and like doing just a raw if statement or like trapping if statement on something is actually not that much slower, or it can be like exactly the same speed or even faster on a modern system than indirect pointer lookups. But on like embedded devices like the Quest, which I very much like, one of the points of JIT compiling a scripting language would be make it run really well on a Quest. For that, branchless coding is on the whole more consistent. So we're still sticking with pointer indirection, like table-based bounds checking. So currently, the way that pointers work is the memory pages are 16 kilobytes of memory. So that's 2 times 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 2. And this is how big our memory pages are in terms of bytes. And the max value of an unsigned 16-bit int. And this is really nice because if we have an array of pointers that is 16 kilobytes long, so we have one memory page, actually technically 4 times the size of the regular memory page because they store actual pointers in there. So that's a lot bigger than this. That's the entire memory size of upgraded computers in my grandpa's day. So that times 8 is the size of a pointer. So this is the size of our pointer page in this system, which I think is still smaller than how many bytes in a 1080 RGB 32-bit image. This is like 8 million bytes for just one 1080 texture, or 1920 by 1080 texture. So this is still drastically smaller than a single texture in a game. So only one of those per thread, basically. And then we're allocating these pages of memory. So then we can do pointers where top half of bytes so pointer is a 32-bit int. Top 16 bits are binding index. Lower 16 bits are the binding offset. So that's like which byte in our memory page do we actually want? Which byte in our actual page do we want to read? Okay. And what I was thinking about is, okay, what if we want explicitly read-only memory and we want to enforce at the runtime level that the runtime physically cannot edit those that read-only memory? Like, it's not a semantic thing. It's not a it gets type checked and then the bit code is still able to edit that if we get a malicious script. No. If you pass read-only memory into a script, I want it to be physically impossible for malicious scripts to edit that memory. the load instruction will only function 4 bytes in a read-only memory range. So I was thinking that we could do something like splitting the bindings, where you would have 8 bytes or bits of 8 bits of readable memory and 8 bits of read-only memory. But the thing is, then you get into, this is 256. This means that we, no, please go away. 256 possible bindings. Minus somewhere in there, I'm gonna have a default page with a like a guard page set. So if you any one of the there's like a if any accidental memory stuff happens, you'll hit the guard page instead of undefined behavior. You will always hit the guard page, and that will throw an error. So, you know, either this is a malicious script trying to do something it shouldn't, but it just hits a guard page. So there's like that default guard page at like 0. That also is like an effective null pointers. If you try to access them by default, that you'll hit the guard page. Possible read bindings, possible read write bindings. And this seems like a lot of bindings, like 256, that is a lot of memory. I am scared that it's not enough memory, because that's 256 times this number. So we have this number times 256. And I think 256 is the max value of an 8-bit integer. And we get 4 million. And let's say that we're interacting with a 4K texture through scripting, and we want to do this on one script. Now, the benefit of having a binding system is we're able to swap out the bindings at runtime as we need to. So I don't think like the entirety of that texture would be in memory at any one time, but in the final version of the scripting language. But when while I'm still developing the scripting language, there's still the chance that like my handling of bindings won't be perfect, and we will need like significantly more bindings bound than we actually need for the runtime to function. So keep in mind, this is our max that many bytes for each. So let's say we're editing a 4K texture, and this 4K texture is 32 bits and has an alpha channel. Actually, you know what? I think it's more realistic, at least for the time being, that we're going to say we have 8-bit color, or 8-bit color channels. So 4 bytes per color times 4 colors, RGB alpha, and then that's times, 4K texture dimensions. Don't worry about it. And yeah, let's say that this is a square texture. So this is times this times that. And, you know, it's not obvious at first, but 268 million is a little bit more than 4 million. Just slightly more. So I think we need the ability to access more. We need to be able to access more read-write memory and more. We couldn't even do a read-only binding of memory that size. That just doesn't really work. The other thing I was thinking about when thinking about like when we are going between different threads will have different bindings contexts, and if we are rebinding and unbinding memory at runtime, we run into the issue of what if the binding index, what if one bit of memory gets bound to a different binding index than it was originally bound to? And what if that binding also contains pointers? So let's say we had a linked list stored for some reason. You're using a linked list in the year 2025. You use the concept of linked lists in a lot of data structures, but you don't use raw linked lists a lot of the time. Anyways, let's say that you have a linked list inside of this binding, and you have a bunch of pointers pointing to the binding itself as it was originally constructed inside of the script that created it. Those pointers would be effectively all wrong the instant you rebind it to a different binding, because the binding is stored in the pointer itself. So this is kind of like the entire point of having the binding system was twofold. Security, only binding the memory you actually want scripts to be able to access, and two, I wanted to be able to access vast amounts of memory from every single script without having to do the WASM approach of, here is a 4 GB buffer, deal with it. And you need to bind that 4 GB buffer for every single script. Not very viable. But realizing that, like, oh no, the instant I try shuffling bindings around, unless I make sure that they are always rebound to the same exact binding, and we know that bindings are never going to clash with each other, like if we start sharing binding indexes, because we ran out of total binding space, oh no, now this binding needs to share the same index as this other binding, because for their pointers to stay valid, it needs to be bound at the same index that it was bound before, but there's already a binding in that instance. Oh no, the entire point of the system is kind of broken. I'm still limited by memory. So, not only would the system mean that there's a maximum of 4 million bytes for one script running at one time, this means that our total memory address space is 4 million bytes for every script in the system. Every script in the system that's ever going to share memory. So if we had completely separate systems that we know are never going to share memory, those could have different address spaces, and that would be fine. But if we need to access any more memory than 4 million ever, like in the instance of editing a 4K texture, and I know some people are even going to want like 8K textures, this ain't going to do it. This system ain't going to do it. But what if we went, 32-bit int? What if we did 64-bit int? Now, all of a sudden, we have enough address space for all of these things. But immediately, we run into an issue. If we wanted to do the split into two pieces approach that we were doing before, our pointer, like our bindings page, like our per thread bindings page, jumps from 131,000 bytes to instead we need 8 bytes times 32. So the size of a pointer times 32. Something's off. Oh, right. Max value times the size of the thing. Right. So the way that we should be calculating this is 2 to the power of 32. So I believe this is the max value of an unsigned int. Let me just double check myself. Unsigned 32-bit int. 4 million, or 4 billion. Uh, 294 million. 4,294 million. Which is what we calculated. Okay, my math was correct. So this is the possible amount of bindings that a 32-bit integer could point to. Now, here comes the fun part. What if, what happens if we take this number here and we times it by the space required to store that amount of memory? This is how big the same exact approach of indirection would work. So bindings pages would be this big, and regular page would not be 16 kilobytes. They would instead be the value we multiplied to get here, this 4 million number. This is a lot more memory. This is a lot more memory to work with. Instead of like, oh, it's 16 kilobytes. This is the entire RAM of a Commodore 64. But in the modern day, it's literally a 0.0 something of a percentage of your entire system RAM. This starts getting back into the range of, bytes to gigabytes. Come on, I know there's a calculator. Methinks this is potentially larger than my RAM can actually handle for a single thread's pointer page. Why don't I just 3-finger salute it? Memory. Yeah, so unless my system throws up a massive swap page, massive swap volume, and starts using my M.2 as RAM. Funny thing, that's still actually faster than OG RAM, I think. On an OG computer system, you could use an M.2 as RAM, and I think it would run fine. But yeah, so we get into a situation where taking the same exact approach, doubling the bit size, is orders of magnitude larger, and we fill up our RAM simply by trying to allocate our bindings page. This is not acceptable. So, what is the solution? How do we handle a memory space larger than our computer can possibly handle, and then also make sure that we bounds check it without, that we do branchless bounds checking on an address space larger than we can allocate for? Well, it's simple. Instead of splitting this 64-bit int into 32-bit ints, we split it into 16-bit ints again. 16 bytes, 16 bytes, 16 bytes, 16 bytes. And this is the entirety of this 16-bit integer. Then, instead of taking the approach we were doing before, where we had a 32-bit pointer split into 16 bytes. And then this is binding and offset. Instead, what we can do and then we have a 16 kilobyte bindings page that this references, and then other 16 kilobyte pages that this points to, and then the offset doesn't offset on. Instead, we can have a 64-bit pointer, and then have 16 bytes. And what we're working with here is, what if we still use that same 16-byte binding, but we just have a situation where we just have 4 pages. Like that. We just have 16 address spaces. Or we can do what I was considering, which is allocating different ranges of memory for different memory types. Now, why would we do this? Why would we allocate different ranges to different sections of memory? Well, it is because it is really easy to make it so a command can't access a certain address of memory. You just do the operation that I'm already doing to split this 32-bit pointer into different regions of memory. I just do the same exact operation that I'm already doing on it, which is an AND operation. So I do an AND operation to get the lower 16 bits of memory, and I do a shift operation to get the top bits of memory. Now, what if... Now, hear me out here. What if this bottom 16 bytes of memory represented read-only pages? So, any range that could be represented by that 16 bytes of memory is a read-only memory page. So everywhere from 0 to 16 KB, every memory binding in this range is read-only. So that's a range of read-only values. And then the next thing we could do is, instead of doing like the super deep nested memory pages that I'm kind of talking about here, I don't think it makes sense to nest memory pages that deep. At most, we should only add a third in, otherwise you like super start slowing stuff down. Not actually, you don't actually start slowing stuff down too much because pointer indirection is fairly fast as long as the branch predictor can branch predict and load memory in advance if needed. So if we go to the next range of memory, which is from 16 kilobytes exactly, so this is actually 16 kilobytes not inclusive, like the max value of a 16-bit integer not inclusive, then I guess it would be inclusive, wouldn't it? That's an edge case. I think if I add the very last bit of that sequence, no, actually I wouldn't be able to do that. That would half the value if I deleted the last value of the sequence. Anyways, actually, I guess we would just not use, we could just not use that value as read-only memory, or just note that like that last binding can be read by the read command. Anyways, what if we used this next range of values here as our readable or writable memory? As our writable and readable memory. I actually want to do some math. So there's two different ways that I could do this system here. And that's do a shift, like do a, I think it's a, is it a left shift? I think it's a left shift. And to reduce to, well, actually I would have to do an and a left shift, I think, because we still have the bytes over here. Anyways, if I directly used this 16 kilobytes as an index in another binding page, just directly, and then we didn't do the second bindings page from the other bytes of memory, actually no, see, I want to have branchless choosing like read-only versus write and read. Somewhere in here I'm going to have to split a top level 16-bit integer. And then we're going to have to do yeah, my ranges, like direct ranges idea doesn't make very much sense because we start adding in ops and like, oh no, we're treating write read differently than we're treating read only, and that's not really acceptable. So instead what we could do Indeed, unacceptable. What we could do is just do this, where each one of these 16 bits maps to another bindings page. And of course, if we don't have anything allocated in a memory space, so let's say this range of these bindings are unused, we can just point them directly to a guard page. So 16 kilobytes of memory that are set up as a guard page, which is an operating system level thing where it just throws an error if you try to access that memory. That's how stuff like stack overflows get detected. Is when you try to read into the guard page, when you try to read into the guard page that is guarded by that is guarding this overflow of the stack. Yeah. Anyways, so we just point all of these pointers here directly to a guard page. So if you try to go down your list of tables to try to find your actual memory to work with, you just immediately hit a guard page and it's like, oh, that memory isn't allocated. We don't have anything allocated in that address range. So we just default initialize all of these values to guard page, and then any out of bounds access automatically gets forwarded to this guard page. And that's how we detect out of bounds access. And hopefully the sandboxing of CraneLift doesn't mess with that at all. I am worried that the sandboxing of CraneLift will mess with this a little bit. Alright. Because CraneLift is sandboxed, so to some extent, so errors don't propagate outwards. Or are they? Do traps occur in the host operating system? Or are they copy? No, I don't call the function through a VM. So it would be impossible for CraneLift to sandbox that, I think. Anyways. Oh, I need to add another thing to my tasks list. I need to add debug info. Because I want to be able to use a step-through debugger on this, even though we won't ever really be using step-through debugging a lot of the time, because a step-through debugger will pause the entire client, and that's not very viable when you're in like networked. If you can't stop the server and the client at the same time, it's hard to debug stuff. So we're gonna have to come up with alternate debugging systems than just like a regular debugger. I do think that either some form of interpreter that we can stop just one system, or something like a stack trace where it just like, here's all the inputs to this function and here's all the outputs of the function, because all of our functions are at the moment entirely deterministic. So you would be able to recreate the execution of a function after the fact if you recorded the input and output values, or just the input. You'd be able to recreate it from just the input. Pure functions are nice in that way. No side effects. But what we were working on, bindings. So, yeah. So this is the actual memory to access within a binding. This is our old bindings page, and then this is a list of pointers to binding pages. And that one extra pointer in direction doesn't add very much cost at all, especially if it's hot in memory. That will not slow stuff down very much at all. The other main thing you have to worry about is data traveling to and from RAM to the CPU, but once it's in the cache, you're fine. And then this 16 bits. I'm not quite sure what I want to do with this 16 bits. I think that 16 bits is where we store flags about the pointer. I don't really want to go... 4 pointer indirections feels like too much. Let's see how much memory you can potentially allocate if you aren't using that last 16 bits of the 16, yeah. If you're using those 16 bits only for flags, how much memory can you access? So that is 2 to the power of 16. And then it's this times itself, right? This to the power of 2. And that gets us up to our 4 billion. So that's the max value of a 32-bit integer. And I think, yeah, this is 4 gigabytes right here. 4 gigabytes of RAM. It's a lot of RAM. Am I doing bits right now? No, this is bytes, because that's that page times that page, so this is bytes. Bytes to gigabytes. Yeah, so that's half of a potato PC's RAM. With just a 32-bit integer. So all of the 64 bits or 64 gigabytes of RAM chads will be satisfied enough with only 3 pointer indirections. We'll be able to access all of their memory and more. So only using 3/4 record for most RAM in a PC. How much more power it has than what was being used to land on the moon? They landed on the moon with a potato. Though that computer is a work of art, because the way they coded it is it's literally a physical matrix of like steel wires with copper wrapped around them, and then like little like toruses of like ferrous material, and the way that they wove it all together is how they programmed it. Yeah, it's crazy. At least that's one of like the space computers, is like physically woven together to program it. So I don't think we're running on a supercomputer. And even if we are, we're not directly accessing all of the RAM at once. Okay, let's just say max RAM that anybody's ever used, it has ever put into a personal PC is 180-ish gigabytes of RAM. Or 120. Yeah, let's say 120. Plus maybe a little bit more. So with using only 3/4 of a 64-bit int, we can access, well, we're well future-proofing ourselves. We can access all the RAM on the PC, no problem. No problems at all. No problems at all. Okay. And this also means I never have to worry about changing the binding position of a page of memory that we've bound, because we have enough binding slots to cover never changing the position of memory ever. And that makes it an easier design problem. So we slot in this one extra layer of indirection between, so we just have binding 1, binding 2, offset within physical RAM, and then we're good to go. Now, why do I still care about these flags here? That's because I don't necessarily want people reading or writing to functions. Dang, I have to put it in here. I have to put it in here, or it doesn't make sense to put it anywhere else. So if we want to do our read-write XORs, we're gonna have to do a read-write call, and like which memory addresses of this you're going to be able to set to be callable bindings. Just what ratios make sense. So let's say 2 to the power of 15. It's a lot less memory space, but we're basically splitting in half. Or a lot less bindings per se. So if we have one flag at the top of this 16 bits, so if we have, you know, our 16 zeros, and I'm not going to draw all of them out, but if we use these top 2 bits, which are the bits representing the very top bit represents half of the max value of this. So if I say 2 to the power of 16 divided by, that's gonna be the same value. Yeah. That's not very large, but I'll bump it up a bit so it's visible on stream. So this bit here represents above or below this number. This bit here represents above or below sorry, not 16 kilobytes, 65 kilobits. is the max value of that. So we would have actually had significantly... I think I've been doing the math right, but we would have had... Some of the statements I said last were inaccurate by a couple orders of magnitude. Anyways, point still stands. Need more memory. So this value here represents this much memory. Actually, so how much RAM would this be? Oh, that's fine. That's a perfectly acceptable amount of RAM. Maybe. Yeah, that is a perfectly acceptable amount of RAM to allocate multiple times per thread. Actually, we're not doing it per thread anymore. Memory bindings. Memory bindings are global now. I've kind of procrastinated on learning more of the lower level stuff after not feeling learned enough from college. The lower level software gets, the more careful it feels like you need to be. It just means that occasionally you blue screen your computer, but like, computers are super resilient, you can't blow them up. Now working on cars, you can blow those up. Doesn't stop people from doing that though. So working with software level stuff, even though it says unsafe, it's one of the safest hobbies. It's very hard to brick your computer through coding. But do we ever think we're gonna have more than 16,000 function pointers active ever? Actually, wait a second. This represents more than 16,000 function pointers, potentially. This can represent this times the max value of 16 times the max value of 16, so we're fine. Yeah, so I think this byte here is going to be our... Yeah, that byte there is going to be our... Is this value a function pointer? And then this value here is going to be is value is this pointer readable? Because that gives our read-write memory the greatest amount of address space. And then this is pointer callable. Actually, does it make sense to have them in that order? Even though this is technically like the larger address space, we want to reserve as much of that for actual variables because we're going to have a lot less function pointers than we do have actual values. If we're talking about this whole is pointer callable, or this isn't even is pointer, this is binding. because it's everything. We're doing this at this level from this 16-bit integer right here. So these two are completely unaffected. So it's affecting all of the memory address space beneath it. So this is bindings readable? Is bindings callable? Then this should be readable. And then this, for the sake of consistency, should be and then I can ensure that just by directly setting this byte, or more precisely ignoring the value of that byte, these 2 bytes, we're never going to use the actual values of these bytes in our actual code. When we read the pointers, we're going to automatically fill in these bytes, and with the exception of the read operation will use readable to figure out which address space to go to. But aside from that, and that's why I wanted to swap them around, is because the read will only XOR, not XOR, it will AND this value here. It won't even, you will either or, or AND, whatever I need to do to make sure that bit is that exact value. And then it's just physically impossible to access the value of a pointer's address. And it's also physically impossible to pass your own value into a spot that's expecting a function pointer, because it will try to read bindings. You'll just directly try to read bindings instead of actually accessing the function pointer that you want to access, or that you try to like construct yourself. So this makes it possible for us to freely pass around function pointers, just like willy-nilly pass around function pointers, and not have to worry about verifying, hey, is this actually a valid function pointer? Because the function pointers aren't stored as actual pointers. They're stored as references to a binding containing a function pointer that the runtime set up. Alright, thank you for sticking around while you could, though. It is appreciated. And this is like the main thing I was procrastinating figuring out before moving on with memory. So, I'm going to say make pointers 64-bit, ignore first 16 bits, second 16 bits, ignore top 16 bits, by default, it's little endian, so the least significant byte of a multi-byte number is stored at the lowest memory address. What about bits? In a single byte, the default common order of bits is consistent across most computers. So it replaces the most significant bit on the left and the least significant bit on the right. So I guess I'm right shifting stuff. I think. Let me double check. Because I can just do that. I am shifting right. I just wanted to make sure my language here was correct. So we ignore the top, or first 16 bits, second, first bit of second 16 bits. Actually, we're gonna say the bit is the callable flag. 17th bit is the readable, or not readable, writable flag. Rest of the second set of 16 bits is treated as a binding index. It's treated as a binding index. Flags are part of the number. And specify the ranges of bindings that have the flags properties. I think that's descriptive enough. I think, maybe, possibly. Third set of bindings. Set of 16 bits is an index into an intermediate binding page. Fourth set of 16 bits is the offset to a byte in a value page, or a function pointer binding in the case of, or function pointer binding in the case of Brane. Work with me here. Function pointer binding in the case of or function pointer binding if function flags are set. Okay. I think this is correct. All right. I will be right back. My mic remind me to turn it back on. A mute button on this? Anyways, remind me to unmute my mic when I come back. Okay, and we're back. Actually, is that button the mute button? So when I'm not... No, that's still... Yeah, it's just, like, makes it louder. I'm messing around with that. I could have sworn that deck had a mute button on it, but no. When you're using that mic, you never want to mute. That's okay, my hair's just gonna be weird. Probably close that door, just so I'm not annoying people throughout the entire house. Blade runner, relying on my tatami mat, which has very little cushion. It's like a... When it was new, it was like 4 inches of cushion. It is not that anymore. It's probably less than 1 inch of cushion now, because it's all been like pressed down. And then I laid up against the wall and had my head at a 90-degree angle against the wall and watched the entirety of the original Blade Runner like that. And I think that's what cooked all of the lower back muscles. That or was the nearly 3-mile run. Either or. Okay. So I think this works. Let's... This is not part of the back end. This is part of core. Let's create a new memory module. Indeed. I'm psyching myself. That is how you spell memory, right? Okay. I specifically bought them so they would cut my ear, not press against them. So they are intentionally very large. Because I hate headphones that actually press against my outwardly flared ears. And there's a lot of headphones that like very slightly press or like fully press against like your ears. It's fine for like 2 hours, but then if you're like me, where you're just on a computer for 12 hours straight or like 14 hours straight, worst or best case scenario, you decide. Yeah, ears not happy about that unless I wear these. Phone dent reveal? Not much of one, I don't think. I can't tell. Here, let me bring up my own stream. Okay, not much of one. What we're doing here? Pub struct. Do I just want to call it store? That is the very Rust thing to do, is call it a store. Alright. Absurd. Went the earbud route, ears kept getting squished by headphones. See, the thing is, I prefer the sound of headphones to the sound of earbuds. Earbuds can be very nice, but like headphones are more comfortable. See, for me, I dislike wireless devices because I need to remember to charge them. What charge are you on? What button do I press to know what charge you're on? Nearly dead. So I have everything wired so I don't have to remember to charge it. Yeah, usually, if I'm out and about, I'm earbud maxer. Okay, so what data are we storing here? Just wear the one earbud at a time so you can still hear surroundings. Yeah, same. Do I want separate data structures for this? I don't think I do. Now, the real question is, are there any potential security vulnerabilities of incorrectly calling functions? If none of the values can cause a security issue, can the function call itself being done wrong cause a security vulnerability? Security vulnerability? That's a good... This is a good chat bot question. If all the if there is no possibility for the humans to a function to cause security vulnerabilities, would a malicious caller of that function in a JIT set be able to cause a malicious outcome for that function, given that they may change the arguments passed to the function, but are use a standard because we can truly guarantee that no argument, including its type, range, value range, pointer, provenance, and even derived side effects like loop counts, can influence any behavior that could be attacked. Then a malicious caller cannot cause a new security violation just by shuffling different but API correct arguments into the call. Yeah, pointers are completely safe. This is completely safe as well. This will be checked as well. This doesn't matter because we're already checking every value type. This is what I'm worried about. If the callee mistakenly uses caller-saved registers without saving them, well, that's the problem of the malicious script blowing up, but I don't care about the malicious script or buggy script blowing up. It's already bugged. It's gonna blow up sooner or later. It's fine if that causes it blowing up. Global state, we don't have global state from the caller. See, this also is problems with the caller, not the callee. Side channels, they just exist, not necessarily. Since I've completely abstracted how the function call works, they can't change how the stack pointer works at all. They can't touch the stack at all manually. We don't have a garbage collector. We do have reference counted handles, but scripting can't directly access those ever. Unless they call the wrong functions, then maybe you leak memory. Maybe. I will not be assuming that a malicious color can cause a security issue. So we can just have direct function pointers stored in a page, which is nice. So what are we storing in this store? We have our pages pool. I can still check if pointer is null. Well, I guess the store is just going to be unsafe, or use unsafe Rust code. But the code is going to be safe because we check it. This is going to be a pointer to mutable vector of well, actually it can't be a mutable pointer to vectors. All of this needs to be basically static. This is a statically sized array, which is what I want. This is a pointer to a page of mutable page of some pointer. Then we also have byte page. System alloc. Then you can pass in a layout. Interesting, so this is keeping track of all the memory allocated in the system. That's pretty cool. But this is what I care about, is unsafe system alloc with a certain layout. Because I want to over allocate or I want to align my memory pages to actual memory pages. I might just do yeah. So this is a pointer page to a pointer page to I don't know, unit? With the page of all bindings, And these could either be a pointer page or a byte page, depending on the range that they are allocated within. Oh, do I need to explicitly say... no, box means it's always... We need a pointer... Actually, wait, this is a pointer page, so it is implicitly pointers. Okay, you just put in value, so you could say pages is box new, and then guard page. Let guard page equal box new. Into raw box new. And then this is a byte page, so I'm just gonna say 0. And then we should probably do an actual OS specific thing for this. But and then here we just do yard page as our default. Oh. Yeah, that works. They are always valid. They aren't null. I forgot I already had this planned. Value page ref. That makes this page a lot larger, but it means we can slot it into anywhere that's, well, yeah, We're going to access the pointer at all, well actually we're adding to the pointer, so we should probably have it be large and, it's fine, it's big. Big page. With a bunch of metal pointers. So our pointer error will have not bound. And unaligned. And this should be a scope lifetime, because we are going to be setting up mutexes for all these pages to make sure that we only ever access them mutably. That's done at the store level instead of at the whatchamacallit. That's done at the store level instead of at the in the data type itself. Like, I love the way Rust scopes values inside of mutexes. But in this case, what are you complaining about? Okay. Complaining that we're not returning anything. It's that song. This song always gets me. Like, oh no, the music stopped. No, it's just that song. Okay. Call that index. There we go. Brane scope pointer is a U64. And now this is unsafe. Gonna put to do on drop. It's okay, we'll be able to do all of our testing with this throwing an error. Okay, then our pointer is of type BS pointer, pointer. Where? Oh, right. Turbo Fish. Okay, so now we... I wish I could do this on the compiler side. But we are just converting this pointer here into an array of all of its indexes. So the first byte of B1 is that should throw an error, right? Because you can only left shift that 15 places. Does Rust have a clean interface for bit flags? Wait, is that a format I can use? You can do bit literals. Oh, that's so much better. That's what I need here. To type out 16 zeros in a row. So it's 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. And that is our bit flag. Dang it, I have the exact same issue as I had before, which is readable versus non-readable bindings. The problem is if we're trying to make it so we never move bindings around, that means when we convert from read-only to read memory, we have to move them. And as stated before, moving bindings invalidates the pointer references. So we can't move bindings to make them read-only. How fast is it to set memory to be read to toggle read between read only and write all on both Linux and Windows. Windows are using Virtual Protect, or NT Protection Virtual Memory. Other system calls to modify the page table entries for the affected region. Both systems generally work at page granularity, typically 4 kilobytes. It can be 2 megabytes to 1 gigabyte. Huge pages. On multicolor systems, this requires inter-processor interrupts to invalidate entries on all cores that might access the memory. Scaling a single page is relatively cheap. Yeah, so it's not viable for what we're doing here, because this still takes, like, that's a noticeable amount of compute time at the scale that I'd need to be doing this. Because this would be basically getting toggled every single time we passed writable memory to... Either we would have to choose, do you want to keep all memory pages in writable state or readable state, and toggle that on and off based on function requirements. This is not viable. It also mean toggling between readable and writable. Either I have the fixed performance cost of walking over the entire 16 kilobyte memory page and shuffling around pointers, and I have to take into account wait a second, I solved this problem. I solved this problem by making it so that functions, or rather, by defining that memory pages may not store pointers in between function calls. They may not store resolved pointers in between, not in between function calls, but in between pipeline calls. They must store page handles, and those page handles that we can have be globally consistent. Okay. So basically, that means we are able to freely move pages around in between calls to functions. If a page has no active locks on it, like if it's not actively being used, then yeah. We do have a way to resolve a pointer, but we also need a way to resolve handles, and that's more important than this whole deal. This is our bindings. Then I'm gonna have another thing here just called pages. I want to make this a void pointer so bad. Apparently this is the correct way to do it, is to have like an opaque type there. Do we just put functions in byte pages? I kind of just want to put functions in byte pages. Doesn't that mean that technically a function pointer +1 would be incorrect? Technically, yes, it would. It would mean that. That's fine, right? But I'm not entirely okay with it because there's like the possibility of reading past the end of that page. Unless I just XOR'd it to multiples of 8. I already have the concept of page pointers. But if I put an option there, it messes up the page layout because I need to be reading this from JIT compiled code and I don't want to have to recreate the concept of the Rust style enum in there, and that would also add in branching. Just really have to transmute this? I don't think I need to transmute this. This seems to... oh, no it doesn't. Those aren't actually working. They're just not breaking. There has to be a clean way to go between references and... that works. Oh wait, this is 0 beating. Say that that's a byte literal. We need a clean way of handling that. Right, U16s are 2. Because it's 8, and then 8. I just did a 4-byte data type by out of sheer habit. But this is fine. Oh, this is actually how they parse this stuff. This has been super useful when I was cloning the Rust parser a while back. No, those are hash literals. Oh well, I guess nobody uses these because they're large, but I want to use it. So I think this is the highest significant bit here. This is the lowest significant bit here. So this is half of the max value of a U16, and this is a fourth of the max value of a U16. If I'm understanding it correctly, which I hope I am. You can tell I haven't been coding in Rust very much recently. Putting parentheses around stuff. Page is an array of bytes. Yes. And there we go. I think this is all the correct operations for our host runtime to safely access um, our own memory and get the pointers. I just realized the entire point of this was the ability to bind bindings per script. Right now I have global bindings and no way to filter between them. Alright. I'm feeling a little bit too low energy to do stream right now. I think I still am going to keep working on this, but this is kind of like I need to sit here and not talk and just like stare at the code for long periods of time as I just like work through stuff. Just a ton of busy work for now. Nothing super interesting now that we already got through like the actual like here's what we're doing right now. I'm rewriting the scripting language to support this. And then we're just doing like the how is our allocator actually going to work? Which writing a custom allocator is interesting. Especially since, well, we're not necessarily writing a custom allocator per se. We're just like binding pages and yeah. Anyways, another stream tomorrow probably. And we'll see how far I got on this. But yeah, till next time. I'm gonna go eat food and then get back to this.